Well, let's get started. So today's lab we'll be discussing image search. In the last lab, we discussed how we can retrieve like audio content. So today we'll be discussing like content-based retrieval on images. So if you're given a collection of images and you're given one query, which is an image, how can you find similar images based on the image that you're given? What technique can you use? Like you're given a collection of images and you're given one query, which is an image, and you want to retrieve images that are similar to the query that you have from the collection. Yeah? Interest point, how? Okay, without SIFT. Yeah. Classify the image, yes. Yeah, what other technique can you use?
You mean like without metadata?
Yeah, without metadata, you're just giving an image.
I think we can if you want to, you mean you want to retrieve the images
randomly?
Sorry, can you hear me?
Like if you have two images, right? You want to compare them. You can, for example, you can represent images as matrix, right? So you just have two matrices. So you can do pairwise comparison using maybe the cosine similarity, or you can even use KNN to find the most similar images given one image, right? Yeah, so that's one technique to use. And again, we called this last time the brute force approach, okay? Where you have your image, you compare with each single image that you have in the collection, and then you will retrieve the most similar one. But we want to do it like in a more faster way, where we don't need to compare our image with every single image, but we want to use the advantage that we have with index, where we can use nearest neighbor search, okay, to find the similar images. So for that, we need features. When we're given an image, how can we locate the most relevant part on that image, right? Yeah, maybe ages, maybe point of interest in the image, okay? So that will be used as our features, okay? So if you have, for example, the location of those features, given the location, like the coordinates, we can then index them, index each point of interest, okay? Maybe using ball tree, using Annoy, okay? Using HWS. And then when we are given that, given an image, we can have all the point of interest, okay? And we find inside our index where we have indexed all the similar images, the point of interest of all the images in our collection. For each point of interest, we can then find the nearest neighbors of those point of interest, right? And then since our image will have several point of interest, we can find the most common point of interest in our collection, okay? And the images that will have the most point of interest in common will be considered as similar, right? So that's the topic of this lab. We'll be using SIFT. SIFT will help us to detect the point of interest in an image. Then we will index those points of interest. After indexing them, we then use those index to find similar images given a query. Okay. Yeah. So can you recall briefly how SIFT works? Can you give a brief overview of SIFT? Mm-hmm. Okay, so the first step is to detect point of interest. Okay, so how did it in the detection step? You basically use what? You have like several Gaussians with several scales. Okay, where you apply several Gaussian with several scales on your image. Okay, so you have like increasingly blur in your image. And then you want to find in that image, you will apply maybe the Laplacian, okay, to highlight the maximum on that broad sequence of images. But since the Laplacian is hard to compute, you will do what? You will compute the difference of Gaussian between two consecutive images that you have in your stack, okay? When you have this difference of Gaussians, you can then use what? You can use like a filter, it can be like a cubic filter on your image. So you have one particular point, you have like the neighbors, maybe the 26 neighbors from the bottom and the 26 neighbors from the top, okay? And from this point, you will choose the maximum, okay? Which one has the most intensity? And that will be used as our point of interest, okay? And you do this here and you retrieve most point of interest. Now, there are point of interest that will be more relevant than others. How it works, let's just run the first cells here. And then we have one example of point of interest, and then we will interpret them. I guess do you have access to this data set? The Caltech 101 data set. We have a link here where you can download it from the link. Okay, this means they have updated the website. You can come to data sets and then you have them here. So you can download it from here. Again, you come data set and then you have Caltech here. And we download them. So once you have them downloaded, you can save them somewhere in your the folder. And then I will use the absolute path. Yeah. I'll have to close this. So we'll be using SIFT implementation in OpenCV, okay? So it's not like embedded to OpenCV, it's like completely separated implementation of SIFT that we can use to detect those points of interest. So the first step is like we take any image that we have, like remember, images are in different categories, okay, in our data set. So we take one image, we read the image with OpenCV, we convert it into grayscale image, and then we instantiate SIFT object. From here, we can then detect the point of interest from the image that we have. So we run these cells, we obtain this one, okay? So you have point of interest, and for each point of interest, you have the location, and you also have the radius, okay? So can you explain what does it mean? For example, if you consider this point of interest, okay? Why does it have like a bigger radius? What does it mean internally in the SIFT construction?
The angle of the feature?
When you locate it, it keeps its shape.
In this case, no, not really. Remember, we have different Gaussians, right? And every time that we locate one maximum, okay, the position of that maximum, because when you have like, how can I draw it? Give me a second. Well, so if you take a look here, does not want to share. I don't know why I cannot share my screen. Okay, so if you take a look here, we have a different scale of Gaussians. Okay, on this scale of Gaussian, when we pick one particular point, we will look at the neighbors in the upper point in the scales, and then we also have the neighbors on the scale down. Okay, so when we pick one neighbor here, if it is the maximum across like the 26 neighbors, the sigma value on this level will be used as the magnitude of that point of interest. And this is that sigma values that will define what is the range around the point of interest. Okay, so this means that if you locate a point in the highest layer of Gaussians, this means the image is maximally broad. Okay, but even when the image is broad, that point is like highly, it's maximum compared to less broad point. Okay, so that we assign like more weight to that point. So it's defined by the value of the sigma that you have in that particular layer. So what does it mean in terms of what we see here? From what we see here, it tells us that this particular point, okay, was the maximum on the highest level of grayscale, okay? And this will give us the value of sigma that we have in that level. So initially we have just the normal image. In the next layer, you have sigma, okay? In the next layer, you have the layer number, for example, k squared sigma, and then you have k cubed sigma, and so on and so forth, okay? So this tells us that that was the last layer of sigma if you had, for example, 26 or 10 layers. And then the points with like very small, that means that those points were point of interest at the first layer. Then let's discuss the angles. So the angles are very useful when it comes to make our detector invariant of rotations, okay? So we come back to it later, how to see when you have a particular point of interest, how do we represent it as a feature, okay? So this means that if we can have access to point of interest, their coordinates, we can then use them we can index them using any data structure that we saw in previous labs. And then using this index, we can then, for a given particular image, we also extract the point of interest. And for each point of interest, we find the nearest neighbors, okay? And we keep counting how many images had the most common point of interest, okay? So that's the next task. For the next task, first you have to define, generate SIFT descriptors. So here we have key points. If you want to use to get the detect to also have the key point descriptors, you can use this one, and then it will return two things: the key points and the descriptors. Okay. So we can also, for instance, print what is the size or the shape of the descriptor. So we can print descriptors.shape. So when you plot, we see that we have 350 key points described by 128 features. Okay. So those are the descriptors that we're gonna index in our structure. Okay. Now, so first, fill in this function where you are given image path. You have to return all the key points and the descriptors of those key points using the same logic as we saw here. Okay. Yes, so I guess you all understood the task, right? What should be done here? So you are given an image, okay? And you need to return all the key points and the descriptors of those key points. Okay? It's exactly the same as we did here. You first read the image, you convert into grayscale, you instantiate SIFT object, and then you use that SIFT object to detect and compute. Okay? You detect and compute the key points and the descriptors of those key points. Does that make sense? And that's why it should be returned by this function.
Hello? Can you hear me?
Do you have the solution? Do you have a solution already? Well, so here you have to read the image. Save it in wait. And next, you have to convert the image into grayscale. So you're given the image, specify the grayscale conversion. So you have color RBG to gray.
BGR.
Yes, BGR. Okay. Okay, the next instantiate the SIFT. The next step. Yeah, so you have the KP and the descriptors. I have SIFT that detect and compute on the gray image and the default parameters. Okay. So next you have this function that will read our entire data set, okay, and create the descriptors of each of these of the image in our data set, okay? While we also keep the file name, the key points, the descriptors, and the categories, okay? And then we will get the top descriptors. So the top descriptors, we return those who will have the most relevant response, okay? Which is basically what is the magnitude of that descriptor from SIFT. That's why we sort them and then we return shape. So when you run these cells, we have to create now our data set where we have all the categories, where we will have also the vectors representation of each file that we have. That will basically store the key points and the descriptors, okay? And we also save the file names of each of these files, okay? So this will take some time. Right. And the next step is, as we did before, we have annoy to specify what is the dimension 128. Okay. So do you know how the descriptors are computed? Why do we have 128 descriptors from the SIFT algorithm? Well, let's discuss that a bit, and then why it's running. So when we are given a key point and we are given the Gaussian smooth of the image, we can compute the magnitude of that particular point. Okay, where you have, if you have an image, if you have a point with somewhere here, you consider this level, which is basically x plus 1, y, and x minus 1, and then you consider also the point from the other side. Okay, you can also compute the angle between them. So the angle, we use the inverse of the tangent, or the difference between the derivative with respect to x and the derivative with respect to y. Okay, so here you have the magnitude of the gradient, and here you have the angle. Given the angle, we can then define a window inside our image. So in the windows, for each point, we compute the orientation. Okay, so you have different orientation for all the points that you have in that particular window. Okay, those angles are computed, are obtained by the tangent between the difference, the division of the derivative with respect to x and derivative with respect to y. And then the magnitude of this gradient of this angle, okay, the size of the angle will be defined by the magnitude of the gradient. Okay, now what do you do? From a particular windows like this, we just have to count. So if we decide that one key point is described by 8 directions, okay, we will do what we will count, like we have, for example, we have up, we have left, we have this direction, this direction, this direction, and so on and so forth. Okay, we then build bins, which means that, for example, for this direction, like for example, for this particular direction, how many points are having this angle? Okay, we count them. After we count, we have some second value. The same for this particular orientation, how many points do we have? We also count them. And then we have like a succession of bins like this. Okay, basically we have 8 bins because we decided we can describe them with 8 directions. Okay, and then what do? we do this for each of them. So we'll do this for this one, and then we'll do this for this one as well. And then we'll do what? We'll just stack them. Okay, so you have the description for the bins for one windows, another window, another window, another window. Okay, so if for our image, we have 4 by 4 cells. Okay, so each cell will contain how many bins? 8 bins. Okay, and finally, the SIFT description will be constituted by the stack of all those bins constructions. So basically, you have 16 by 8 directions that will give us 128 dimensions. Okay, so if you have 2 images, you will do the same operation where you will compute those directions, the orientation of the gradients. Okay, and then you have like 2 bins where you can match them together. Okay, the most similar key points are similar. So you have 2 key points that are having the same orientation with the same magnitude of the gradient. Okay, basically they are the same point. Okay, so how do we make it invariant to rotations? So if you have, for example, this particular key point, okay, you can see that this direction is most present. Okay, this means that there's like edge. If you take consider image of edge, there's like one edge that is having much in that particular direction. Okay, so such that the representation, if you have something like this, and then you will have like several values. You have this count, like this. And for this particular one, we have this orientation. Okay, so if the image is rotated in another image, okay, you will still have that particular gradient that will be the most relevant in that particular rotations. Okay, so what you do, you can just rotate one image to the direction of the most of one other. This means that you can basically rotate the image and have the same things. Okay, because they have the same variations from the orientation of the gradients. Okay? So at the end of the day, you have this self-descriptor where you have each quadrant that will be described by 8 bins. Okay, and these are just values. How many times do we have, for example, this direction? So this direction is most present in this particular windows. Here we have mostly these directions. Here we have mostly this one, and so on and so forth. Okay, so you have 16 by 8 dimensions that would describe our particular key points. Okay, and for one image, we can have several key points, and those key points will be used as all the point of interest in our images. Okay, so that's why we are in our safe construction, when we got descriptions. So when we keep description, it has 350 key points described by 128 features. Okay, and those features will be basically just the count of the gradient direction of each particular point of interest. So, well, the next step, when we have this, we can then build our index. So we index using 128 dimensions. We're going to index every single key point. Okay, such that when you're given an image, you have one key point, you can extract the neighboring key points to that particular key point. Okay, so let's run the next cells. We are using Annoy. I hope you remember what it's about, where we add all the items that we have in our vectors presentations. Okay, and we also have a lookup where we assign basically this vector is assigned to this particular file. Okay, so one key point is located in this particular file, such that when we retrieve the neighbors of one particular key points, okay, we can have the name of the files that contain those key points that are inside the neighborhood. Okay. Well, so we have our index built, and we build the index with 100 trees. Okay. Next, we need to implement the search functions. We are given an image from the vectors, because remember, we have all the vectors of our image. We have built all the vectors of the images, basically just the key points of the image. So we are given one image, so we have vectors. So what will vectors contain? It will contain all the key points of that particular image in 128 dimensions, okay? So what you need to do here, you need for each key point, you need to find, let's say the 10 neighbors, okay? When you have the 10 neighbors, you need to count them. Like you count them by files. You have one file name, this neighbors belongs to this file name, okay? And you just count how many times one file got like similar key points with our query, okay? So you look through all the key points, okay? And you keep counting. So you can use a counter, that will have as key the file names, okay? And the values will be the number of key points that got that match together. I hope this is clear. If not clear, I can clarify again. And once we have that, we just return the most common one, okay? And the most common one will mean that you have one file, another file, one image, another image, and they have a lot of common key points, okay? So this means that those images are similar. And we are doing this not by doing pairwise comparisons, but using the indexes, okay? So go ahead and fill in that function, and then we will discuss the outputs. Is it clear for everybody? If it's not clear for you, we can again clarify. So here you can see one example of matching. After building the key points, you can then, using two bins, you have two sequences of bins, right? You can compute which one is most similar to which one. You can use maybe the L1 distance, okay? Or other matrix to find which one matches the most, okay? When you have perfect match, and remember, they're insensitive to orientation and scale, okay? So you have, for example, one particular key point that will match to another key point, okay? And what we are retrieving is that we want to retrieve the image that we have the most matching key points, okay? But we are not doing pairwise comparison. Because if it's pairwise comparison, you can just compute key points of one image compared to another image, and you count how many key points they match together, right? And then you sort them to the number of key points that matches. But we saw that this is very time consuming. We want to do it faster using indices, okay? So when we built our index, in our index, we have all the key points of all the images are inside our index, okay? Such that if I'm given one particular key point, I can retrieve the 10 similar key points in the entire set of images, right? So our query will just find the most similar key points to all the key points of our query, that is our image, okay? And then count. Like you have one key points that were also present to 10 other files, okay? So all those files will have +1 +1 +1. The next key points, how many files, what are the neighbors of these key points? We have the neighbors, right? And for the neighbors, we know the files. Okay, so we can keep counting. For each key point, how many files got matched by using the nearest neighbors from our index. Okay, and then we keep counting. At the end, we sort them by the most common one, and then we have the reply to our query. So online, when the meeting ends, please join using the same link. So when querying Hanoi, you can consider using the 32 neighbors, 32 nearest neighbors.
Okay.
Not 10, use 32. Yeah.
Okay, here I'm like using the counter, but like getting the index. But like, what should I do with this index?
It's better to use the file names such that you can later on easily know which image is associated. Remember, we have sculptor. Remember, we have associated lookup. We have a lookup here, and they have the same IDs. Okay.
Okay,
So you can look through the indices that you retrieve from share.
Now use the go
Yeah,
to
yeah,
the
look up and then get the file name. So you will have your counter will be associated with file names and a number of accounts. Okay. So instead of having these IDs, you have the file names.
Okay, but like I have to, first I have to, you mean I should count the file names?
Yeah.
But I don't understand because first you need to find the count the numbers.
Yeah.
in the
So
dictionary.
here you have a point of interest. Okay.
Mhm,
This point of interest has 32 neighbors,
mhm,
and those neighbors can belong to different files.
mhm.
Okay. So you just want to count like this file got one more neighbor in the
Okay,
neighborhoods. Okay. And then the next point again, and then you sort them. You just return the most common one,
Mhm.
and then return the most 10. The most common, the 10. So again, remember when we were building our annoy index, we built also a lookup, okay, where we associated the file names to every IDs that we created, okay? So when you also query annoy, the counter should should count the file names, okay? Not just the index. And you can have the file name using the index. So lookup will have the same index and you get the. So when you have the nearest neighbors, you look through the IDs and then you count the file names, associated file names. Please, if you have a solution, feel free to share. Yeah, you send a message. Okay, it's better to return tuples. It's better to return the tuples, not the array itself. Looks good. But how do you count the most common one? The most common, like the file that we have the most common matching in the key points. Okay. So you saw them in terms of matching. Okay. Okay, good. Right. So let's go and then we compare with what you did. If there's something that you missed, let us know. So let's use a counter. So we use a counter, okay? We not counter, so we use a counter. So for each vector, for each key point, let me call them key points. For each key point in our vector, okay, what do? We need to find the indices of the most similar one, okay? So we have our, how did we call our index? Annoy dot get by vectors. Those are vectors. What is the vector? The vector is our key point, okay? And we want the 32 neighbors, okay? So when we have this one, we want to count by file names, okay? So each index here has a lookup here, okay? So we can then call, for example, c.update as you did, yes. C.update, but we update using file names, okay? So we update using the lookup of I. We take the file name, okay, for I inside our, and I can zoom in. Okay, so we have this. Afterward, we can then, for example, return the sorted oops, which here. So we can sort using XS. Or 30x in our count, where we get the most common. Let's say we want to get the 10 most common one. So in your implementation, return just the 10 common one, not everything. Okay. And as we have the parameter key here, this parameter will be specified. Okay. So when we query, we want the k common one. Okay. So for this step k common one, we also want to sort them in reverse order. Okay. So let's make this as quickly. So that's it. That makes sense. So the principle is pretty straightforward. You have a counter that will count for each file name. You will associate the number of matching in key points. Okay. So the number of key points that fell into the neighborhood of the key points of our queries. Okay. And then after counting them, you sort them, okay, in terms of number of matching, and then you retrieve the most common one, okay, the top key. So let's test this. We have one example of file. We want to retrieve the top 10 common file that are most similar to that one. And then let's run this. So we have these files, okay, that are similar to the file that we created, okay. So let's plot those files to see how it looks like, or if they're even relevant to what we did, okay. So let's plot them. You can put them like 10 like this. Okay, so let's say a figure, we try to use not the plot, but subplots. So in subplots, we will use 1 by 10 plots. Okay. So for each image, so here we have example, we have Okay, we have the file name. Okay, so we have file name. Wait, the results. Okay, our result looks like this. Okay, so we have the file name is here. Then we are not going to use the first one. So file in our result. This is result in plural. Okay. So we just plot. So I if x dot plot. No, image img show. If I'm not mistaken, then we just show that file. Okay. But it's not absolute G. So we're gonna show from our image G. Okay, we have image G where we concatenate slash and like this. Okay. Okay. So let's run this out. What's the issue? Okay, so let's enumerate. The two we're given. This is subplots. Yeah. Im show. Okay, thanks. What's the next issue? Yeah. So wait. That's a bit stupid, but a bit. So let's load the image. So this should be the image. So let's call this img, img will be cv.inRead, and we specify the password. And then we show the image. Well, so this is our query. Let me increase the size. This fit size. Let's make it 50 by 50. Okay, well, so this is our query, okay? And these are the file that has been written. And they are ordered by number of matching, okay? So strangely return an airplane, okay? Because they can be just matching that are just like coincidence, because it does not use the semantic. Just look at the point that match to each other, okay?
Maybe the tail of the airplane.
Pretty nice matchings, okay? So what you can do, we can plot. You can see there's a description here where we can plot like those matching, connect them together, okay? And see why is that the airplane was returned. And you see that indeed there was a lot of matching, okay? So you can find it
Sir, can you hear me?
somewhere. Yeah, you have draw match, so you can check this here. So where you have two images, not this one, we're using SIFT. So you have two images, we will get like the descriptors of those SIFT images, okay? And then you will use the matches, okay? And then you have something like this, okay? So you can do this by your own to analyze why is it that the two image matches, okay? And what is interesting is that this SIFT is really scale invariant, rotation invariant, okay? For example, you have these images with this rotation can match with another images which is located at a different place, okay, in different rotation. So I will let you do it by your own. So well, that is the drawback of SIFT, okay? It is not aware of the semantic. You just look at the key points, okay? And then you compare bins, because you know the bins is just counting how many orientation match to each other, okay? So you can have 2 points that have nothing to do to each other, but they just have like matching in the bins, okay? So it does not account for the semantic itself. So this is our image retrieval model, okay? You remember the assessment that we saw in the assessment, during the assessment lab, where we can use the discount cumulative gain, compare how relevant it's our retrieval. For example, we are given strawberry and we retrieve airplanes. Okay, so we have the category. What we expect is that we would like to see more strawberry inside the retrieve images, right? And then we have also things that are not relevant. So we can use the DCG to assess how good is our retrieval system, okay? Such that we can compare two methods, okay? We have one method that we use neural networks that we will see soon, okay? Another method that we use SIFT, okay? Compare which one is indeed most more performant in terms of quality of retrieval, okay? So here we consider the category as the category is considered as the if the image that was retrieved by our index, they have the same category, then there's a relevance. If it is not, then there's no relevance, okay? So something that we can do straightforwardly here is, for example, have a function that will return the get relevance, okay? And then you have the images. What we expect is to return an array where you have 0 if there's no relevance, 1 if it is relevant, okay? By just comparing the categories. And then you have those relevance matrix. We can use the DCNG that we computed in the previous labs, okay, to assess and return the score. Does that make sense? So if I have the image here, I can, as we did here, as we just did here, one second. So as we just did here, I can retrieve like the most similar ones, okay? Given the image, okay? And then I have the relevance. I have the relevance that is just a matrix. So first, I need the category of my image, okay? So remember, the images are like this. The category is the first before the slide, okay? The slash. So what we can do is have the query category that will be equal to, you take the image, we split using the slash. We split using slash, and then we retrieve like the first or the last one. So you can just use 0. Okay. So when you have the category of the image for all the similarities that we got, okay, we then look through them. So for AMG in similar, what we do, we compare if AMG of 1. So if AMG of 1 is equal to, so again here you have to split with slash and retrieve the category. If the category matches the category of our query, okay, we just append relevance, we append relevance 1, okay. If it is not, then it's not relevant. So we have relevance, we append 0, okay. And then here we can return relevance. Let's indent. Okay. This one is not well indented. Okay. So this means, for example, if we print the relevance of let's pick up the same query as we had here. So you want to check the relevance matrix or vector of this one. What do we get? That's a mistake somewhere here. So we have 1 0 1 1 0 0. Okay. To assess the performance of this ranking, okay, we should have what? The most relevant images should have the most common key point matching, right? So there should be a rank at the beginning, okay? But in our case, it's not the case here. But let's say you have this set of, you have this bucket. So there's a bucket. This is like the bucket of the queries, okay? We retrieve all the relevance vectors, and then we compute the average normalized discount cumulative gain, okay? And then we assess how good is our retrieval model, okay? So what we expect is that the most common key point matching should be with the really relevant image. So images from the same category should have the most common key point matching. If they don't have the most common key point matching, this means that they should be less relevant and therefore rank at the end, okay? So let's just create a bucket of some of these. So you have buckets where you have all those queries points. So I'm just copying from share. And then we will assess this by using our eyes. Well, so let's just for query in our bucket. So we can have like a relevance map. We have this where we append the relevance of this one, okay? And at the end of the day, we just print our relevance matrix for each of the queries. Okay, so you can see that for the first query, it indeed has a lot of matching, okay? And they are ranked at the beginning. So if you compute the normalized discount gain of this one, should be higher, okay? But since we're going to average these values, okay? It will have like different impacts. This one, because this one is ranked not at the beginning, we have lower score, okay? This one we have like what value? Perfect value, okay? Perfect, the ideal discount cumulative gain. So using this one, you can then use the function that we defined in previous lab to return the score. But from our ISIS, we can see which are relevant, which are not. So even if SIFT is not aware of the semantic, it's still doing a good job by discovering features, okay? But we cannot completely rely on it because it will give you most of the time things that has nothing to do with the query itself, okay? So if you query strawberry and you have airplanes, the user will just be frustrated, right? Yeah, so we need like more sophisticated way to detect the features, okay? So for that, we can use techniques from deep learning where we have supervised learning, okay? Where we can say every image has like class label, okay? And the goal is to associate those features to that particular class label. It will not just be because we have bins that match to each other that we say they are similar, no. They also need to have those bins that we match, and they also need to match the labels, okay? So that we can retrieve like images that will be indeed relevant to a given query, right? So the next part, we'll be using any pre-trained model. We have pre-trained deep classifiers, okay, that have like embeddings. And for this pre-trained classifier, we can give them any image and they will classify them, okay? For instance, we can use YOLO 5, which is depending on the size, on how deep the model is and the amount of data that is used. One popular one is VGG, that is also widely used. So if you have PyTorch installed, we can load the model. It's already embedded in PyTorch implementation. You have the pre-trained models, okay? Since you have the pre-trained models, we can use them to classify. But remember, a deep neural network has an embedding space, right? So I don't know if I can have the architecture of this example share. Architecture. Yeah, but let's find where we have the dense layer. Yeah, so for example, let's look at this one. So this is the VGG 16. It's like state of the art architecture for image classification. Okay, so we have several convolutional layers, and at a certain place we have like the dense layers. Okay, so these dense layers kind of encode, provide an embedding of the images that was used. Okay, so if we can find the images, we can use this embedding because they also encode the semantic of the image itself, right? So we can use this embedding as the representation of our image. You have an image, you pass through the network, you do not classify, but you want the vectors, okay? So you have those vectors that will represent our images. So instead of having the 128 vectors from SIFT, we can have 128 vectors from a deep neural network that has been a pretend deep neural network, okay? Then you can have one image, another image, you have their respective embeddings. And then we can index those embeddings, okay? And still perform our retrieval. It will be aware of the semantic. The same as we're using for text retrieval. For text retrieval, we sometimes just count the frequency count, okay? But it's not aware of the semantic. If you have two sentences that are similar, if you query with, for example, happiness, okay? You will not retrieve something talking about joy, okay? Because there is no frequency of happiness in that particular document. But when you have the embedding that can also encode the semantics such that in your embedding, what as male, female will be close to each other, okay? You can then also use the advantage of this embedding to have a better system, okay? That will also account for the semantic of the word. So if you query something like happiness, you will retrieve things related to joy, sad, and so on, okay? So it does not just use the frequency count. The same with SIFT. SIFT just look at the points that we have the same pattern matching of bins without semantic, but deep neural network, we also have the embeddings where we can account for the semantic, okay? So that's what we're going to use here. So we define, we give a file. When you preload, you load the pre-trained models, we give a file, and it can give you the detections that was found in that file, okay? Like most likely in this file, there's a cat, or most likely it is a dog, okay? But these are being pre-trained in a bunch of data, okay? So one advantage of SIFT does not need any data set to train, okay? It's just a sequence of steps that we do to find the features. But for deep neural networks, you need a bunch of data that are already even labeled, okay, to train. So let's pick up one example in our set of data. Let's say I will get accordion. For example, I can copy the path, you pass there. So the model will provide you, I need the absolute path. The model will provide you with, or I can use MGG plus this. Our model is not defined. Let me load the model first. So it has just used the cache of the model because I ran this before, but otherwise it will run for you. It tells you also how many layers you have and how many parameters are there, okay? And then when we run this, what does it tell us? No file. There's a kind of repetition. Let me just remove this part. So there's no found, nothing found. If you print, okay, no detection. Okay, after that, we will discuss why we have this value. Let me go to something that can be much more plausible to find. Let's say we have faces. For example, this is a face, okay? So we want to use this one, we want to query that one. So let me just get one random face. There are too much images, okay. Let me just pick one random face there, and then we use it here. Now there's the detection with some confidence cells, so it has 90% confidence that it is a person. Okay, so you can have the statistics. It tells you that there's a person. Okay, with 91% of confidence. Okay, so the model is pretend. You can also test with some animals. I don't know whether it's the cat or roster. Let me copy this one and paste it there. And then when we run, again, I have issues with paths. Why is it that it copies like very weird way? Okay. Anyway. So it's also not detected. So here we have our data set, okay? And we want to use that model to predict the categories in the data set that we have. So in the next cells we look through all the file names that we have, and you want to detect the categories, okay? So let's run this one. And for this image, it has detected this is the category, this is the return category from the model, okay? The same for this one, strawberry, detected properly. So you have category names of the file and have the tags. Well, for this one, there's no detection, okay? For this airplane, well detected that this is airplanes, okay? The same share, airplane. Piano does not detect, okay? The same share does not detect. You have memorand, and this is seen as a clock. I think from our houses, this is not a clock, okay? So there can be misclassifications. And the same, so we can see that there's a lot of them that are not detected, what is seen as plants, bird, okay? Umbrella not detected, and so on and so forth. So the question to discuss here is like looking at the result. Can we use this for retrieval in the same way as we use SIFT features? Can we use them in the same way as we use these features? Who is for yes? Can we use it as we use SIFT? Yes, like you have the embeddings, right? Can we use them as we use SIFT for the retrieval?
No.
Why no?
Because like we are not getting any, for example, percent similarity. We're just comparing pairwise.
We're just comparing pairwise. But if we can compare pairwise, we can still use the index to avoid comparing pairwise, right? Remember, this model can give us the embedding, okay? And the embedding is a fixed vector size, right? So for every image, we can have the corresponding embedding, right? So as we have the corresponding embedding, we can then do what? Like you have the model, it has several layers, okay? You can just take the layer before the classifier part, okay? Because you have the dense layers and then you have like the classification, okay? You can remove the head of the classification and you have the dense layer. And that dense layer has like fixed size output, right? So this fixed size output can be looked as our embeddings, okay? And this embedding will give us like the representation of the image itself. So we can do what? We can index using the embedding provided by the neural network. Okay? Does that make sense? So we can still embed them, and as we did with SIFT, find the most similar, and so on and so forth. Okay? But there's an issue. What if the labels are different from the original? And also, what if there are multiple or there are no labels?
We can like retrieve them. It's going to be similar to each other. It's
What
going
if
to
the
be
labels
similar
are
to each other.
So first, one issue with this approach is that before having the embedding, you cannot embed something that hasn't been seen before. Okay? So for example, you have a lot of classification that are having none. Okay? Because this data wasn't inside the data set that you used to train the model. Okay? So you have one model. To have the embedding, you should have seen examples of this kind of data before, of this kind of image before. Okay? So your model, your embedding can work well on the images that has been used to train the embedding. Okay? But for missing images, you have no result. Okay? Or at least just random result. Does that make sense? So first, your neural network that you use are trained on some specific images with specific categories. Okay? If you don't have those images and categories in the training set, okay, you cannot have like a good embedding of those particular images when they are missing. But SIFT does, can always provide you the most relevant points. Okay? Well, so but what you can do is like in your embedding, if the image is missing, you can combine them. You can provide the embedding using what SIFT provides, for instance. Okay? Thanks. And next, we have other method that we use image to vector that we indeed do what I just described to you. You're given an image and you will return the embedding of that image. Okay? And from the embedding of the image, we can then, so you embed the image into 512, okay, features. Using that, we can then build the embedding vectors and stack them together, okay? So after getting the vectors, we can use the pairwise distance to compare the embeddings, okay? So if you have the embeddings of two images into 512 feature vectors, okay, we can use the cosine similarity between each of those embeddings. The most similar images, okay, will be assigned with the highest values. Okay. So here you have to define the get vectors that will return the embeddings of all the featured images that you have there. So here you have to look through the images and do the same as here. We get the vector of the image that you use fill to load the image. You get the vectors and you have a stack of vectors for each images. Okay. Compute the embeddings, and then you can compute the pairwise cosine comparison similarity between each of those images. Okay, and you retrieve the top common one. Okay, the most similar one. Does that make sense? Yeah. So we still have some time left. So fill in this method, and then let's see the result. So before the meeting ends, I think we still have 5 minutes left. So in get vectors, this is something you should do something like this. Just briefly discuss what you're doing. So you look through each image and you append the embedding of that images. Okay, and then you can you append the instance of that image in RBG, and then you can get the vector representation of each images inside this matrix. And then that's it, you return them. When you compute the pairwise comparison of each of those images, and then we plot them, we see that in the diagonal, since they are the same images, they will have like a lot of matching, okay? Also in the other position, you still see that a lot of images matches to each other. So you can sort them in terms of pairwise distances and then retrieve the top, most common one. So after writing that part, you should have something like this, okay? You can complete it by retrieving also the most similar point after sorting them. So meanwhile, let us record the attendances. Okay. Just came on. Online, please scan the QR code. If you can't, please send your email in the chat. Well, so that's pretty much it for today. We can wrap up share. Hope there's no, if there's no question. Yes. Convert the image to the last part. Oh. Here. Why do you need? 12 GB, yeah. Because this expect like image with 3 channels. So I will stop sharing. See you next week.